Ok. Mi dimentico sempre. Ok. Allora. The situation is also more complicated. Why? There are allosteric antagonists. This means that some antagonists can interact not with the active site, but with an allosteric site outside the binding site. And this interaction can modify the tertiary structure of specific protein. And in this case, you see this type of curves. But once again, you will see more information about this investigation during the course of pharmacology. We have seen the pharmacological approach. In this case, we need animals, we need isolated organs from animals, and so you can imagine bioethics problem involving this type of experiments. The cost of these experiments. There is another type of approach. In this case, we do not need any animals. It's called biochemical approach, and in this case, we need a receptor, but this receptor is biosynthesized, is cloned, and so it corresponds to a particular protein, and it is biosynthesized by a cell. It's possible to buy a lot of different receptors on web, so it's not so expensive, this approach. But in this case, we have the receptor immobilized on a matrix. We need a radiolabeled agonist. Why we need this type of compound? Because we need a measure of the ability of a specific compound to interact with a specific receptor. So we have our receptors immobilized on a matrix. We put inside the system our radiolabeled agonist. We wash. And then we measure the radioactivity. We use increasing concentration of a radiolabeled agonist, and we get the same curve that we had with the other system, the other approach, the pharmacological approach. You see, just a moment, this curve is the same. In this way, we have information about the ability, the capacity of specific ligand to interact with a specific receptor. But also in this case, the curve is not accurate. In this case, we have on the y-axis radioactivity, you see, and concentration on the x-axis. We can change once again the concentration in minus log concentration, and we have again the sigmoid with the inflection point, and the inflection point is related to the effective dose of 50. The same mathematical treatment that we have seen in the other approach. In this approach, we have to use a radio-labeled ligand, so we have to introduce radioactive atom inside our molecule, and sometimes it's not so easy to introduce a radioactive atom inside our agonist because we have to synthesize again the molecules. We have to use radioactive compounds in lab, so we have to put to increase our attention during the workup because you know we use radioactive compounds. It's not so easy to use this type of compounds, of atoms. There is another approach. We can use a radioactive ligand, an agonist that we know, for example, radioactive acetylcholine. We incubate radioactive acetylcholine with our system, receptor on the matrix. We wash and we measure the radioactivity. And then we incubate with our agonist without any radioactive atom. And we measure the ability of our ligand to displace the radioactive acetylcholine on the clone receptor. This is another way to know the ability of our agonist to interact with a specific receptor. Also, in this case, we have the same curves that we have already seen. The problem of this approach is related on the information that we can obtain from this type of experiments. Why? In this case, we measure only the ability of a single ligand to interact with a specific receptor. We do not measure the ability of this ligand to activate the receptor. So, in this case, we know only the ability of our compound to interact with a specific receptor, but not the ability of this compound to activate the receptor. So, with the biochemical approach, we are not able to know if our molecule under investigation is an agonist or an antagonist, because we do not measure a final effect. We measure only the ability of this compound to interact with a specific target. This is the main difference between these two methods, these two approaches. The pharmacological approach is more complete. We can have complete information about the nature of our compound, if this compound is an agonist or not. In the biochemical approach, we have information only about the ability of this compound to interact with a specific target. Is it clear? Okay. So, hello? These are the two last slides of this chapter. Have you any question at home? No? Okay. We can close this chapter. Okay. And then, just a moment. Oh, where are Now we have the last part of the introduction part. And this last part is based on stereochemistry, but also on other types of isomerism. Why? Why Tumiatti refresh us again some topics of organic chemistry? Because these topics are very, very, and once again, very important in medicinal chemistry. The first isomerism that you know is the optical or configurational isomerism. You know perfectly that one molecule can exist in two forms. One is the mirror image of the other one. The most common case is related to the amino acids. You know, natural amino acids belongs to the L series, and the non-natural amino acids belongs to the D series. This means that normally in all proteins you find L, amino acid of the L series. This means that particular bacteria can use amino acid of the D series if it wants to defend itself from the attack of our enzymes. Because the binding pocket of our enzymes is not able to accept the amino acid of the D series. But why stereochemistry is so important in medicinal chemistry? You have discussed a lot about the interaction of a compound with a target. And normally targets are enzymes or proteins, and all enzymes and all proteins are chiral. Why are chiral? Because they use amino acids of the L series, alpha helix, beta sheet conformation. You know the different shapes of the protein in the space. And these different shapes are due by the amino acids present in the long chain of the protein. So this means that chirality is an important quality in medicinal chemistry. You know the term D, the meaning of the term D and the meaning of the term L. You know the meaning of this plus and this minus present before the name of this compound, glyceraldehyde. And you know also R and S. You know the Ingold rules. You know that R and S are not related to the plus and to minus. Plus and minus are related to the ability of each compound to shift the polarized light. There is also another important rule: the number of asymmetric carbon atoms present in a single molecule. These rules says that the number of stereoisomers is due by 2 to n, where n is the number of asymmetric carbon atoms. In this case, you see you have 2 asymmetric carbon atoms, you have 4 stereoisomers. 2 and 2 are enantiomers. There is also a particular exception if there is a plane of symmetry inside the molecule. You have 2 asymmetric carbon atoms, 2 chiral carbon atoms, yes, but only 3 stereoisomers, not 4. Okay, this is an exception. But why chirality is so important in medicinal chemistry once again? Here you have the chemical structure of 4 stereoisomers of an antibiotic called chloramphenicol. Chloramphenicol is quite old. It was discovered in the 50s. But it was important because it was the first antibiotic synthesized completely in a lab. And so no fermentation from bacteria, no, nothing. So in that time, we had tons of this compound available for the population. You can see in this chemical structure, we'll see this molecule later during the specific part of the course. There are 2 chiral carbon atoms. And so, following the rules, 4 stereoisomers, 2 by 2 enantiomers. So we have 4 stereoisomers of chloramphenicol, but chloramphenicol is only 1. Is 1 air, 2 air, is this first one. You see the antibacterial activity is 100. In this case, we have the MIC 50 value. The other stereoisomer have very low antibacterial activity. Only 1 is potent. This means that the target requests this type of stereochemistry. And the other are not active. And following the rules of the pharmacopoeia, they can be toxic because they are not active, and they have to be metabolized by our liver, and so they are considered toxic compounds in the mixture, if present in the mixture. So it is necessary a very high purity of a chloramphenicol without the other 3 stereoisomers. Here you have another more complex example, morphine. We'll see morphine at the last of our course, in one of the last chapter. You see, the chemical structure of morphine is very complex. 5 ring systems fused all together. How many chiral carbon atoms are present in this structure. We can start from the number 1, 1, 2, 3, 4, no, because these 4 atoms are located on an aromatic ring, and so you know, not possible any chiral atom. 5 is the first asymmetric carbon atom. 6 also, and so 2 carbon atom, asymmetric carbon atom, and then 7, 8, no double bond. 9, yes, the third. 10, no, 2 hydrogen atoms here. 11, 12, no aromatic. 13, yes, 4 different substituents on the same carbon atom. And 14, so we have 5 chiral centers on the same molecule. 32 different stereoisomers of morphine, but only one is morphine. Only one is active. So you can understand the importance of the stereochemistry in the interaction of this compound with its target. But why stereochemistry is so important? You have here a picture. Molecule compound 6, you see A is able to interact with the A site, B with B, C with C. We have an optimal interaction of compound 6 with the target. What happens if we change the configuration of this carbon atom? We have the situation of compound 7. In this case, D should interact with A, and so B with B, C with C, okay, but D with A is not possible. So in this case, we have not an optimal interaction with the target. These are the 2 situations when we have the 2 enantiomers. Here you can better understand this fact. This chemical structure is adrenaline. Adrenaline is very potent, you know, is able to increase the frequency of our heart, okay, vasoconstriction, it is able to increase the blood pressure, and so on, okay. In the structure of adrenaline, there is an asymmetric carbon atom. You see here the star. And so we have the 2 stereoisomers, the 2 enantiomers. Sorry. In one case, on your right, the protonated nitrogen atom interacts with the anionic site. Perfect. The aromatic ring, the flat surface of the aromatic ring is able to interact with the flat area, okay. Hydrogen bonds of the 2 OH, okay. But in this case, we have an additional bond constituted by the right orientation of this alcoholic group in the right position to give an additional hydrogen bond with the target. What happens with the other enantiomer? You see nitrogen with the anion, protonated nitrogen atom with the anionic site, okay. Aromatic ring with the flat area, 2OH catechol group, okay, but the OH, the alcoholic group, is not in the right orientation, is outside is to the other side. So in this case, we have not this additional bound with the target. The activity of this last enantiomer, less active, is comparable to that of dopamine. Dopamine is the same molecule without OH. So you can understand from this example the importance of the right configuration of this carbon atom. Only minus adrenaline, epinephrine is the same, is active, is more active. The other one, the plus adrenaline, is less active. Here you have a more complicated situation. Ephedrine. Ephedrine is also an agonist. This is the chemical structure of ephedrine. Looks like noradrenaline. You see the OH in this position, the nitrogen atom, just a methyl group on the carbon 1. Here you can see two asymmetric carbon atoms, two. And so we have 4 stereoisomers. 2 by 2 are enantiomers. Which are the chemical physical properties of the enantiomer? They have the same chemical physical properties, the same melting point, the same solubility. What you want? All properties are the same, except the ability to change the direction of the polarization line. This means, just a moment, sorry, and you see another term, diastereoisomer. Isomers, we say diastereoisomers, enantiomers, diastereoisomers, okay. Diastereoisomers have different chemical physical properties. This means that it is easier to separate diastereoisomers from enantiomers because they have different solubility, different physical chemical properties, different RF on the chromatography course, and so on, different retention time, what you want. The problem is related to the possibility to separate the enantiomers because they have the same properties. This is an important problem because in medicinal chemistry we need pure compound, pure enantiomeric compound. This means that we have to spend a lot of money, a lot of time to separate the two enantiomers and you have only one of the two, the more potent of the two enantiomers. Once again, you can see in this picture the importance of the right configuration of the asymmetric carbon atom. Once again, you see in this case a noradrenaline. The protonated nitrogen atom is able to interact with a minus carboxylic acid residue, ionic bound. Once again, the aromatic catechol ring is able to interact, pi-pi interaction, with a residue, aromatic residue of a phenylalanine, pi-pi interaction. Okay. The 2OH, catechol OH, one with the serine 212, you see hydrogen bond, and the second one with the serine 209, okay. And once again, you see the OH located on the asymmetric carbon atom able to interact with the serine 169 to give an additional hydrogen bond. Only this type of enantiomer is able to give this type of interaction, the other one not. So you can understand the importance of the right configuration in the asymmetric carbon atom, on the asymmetric carbon atom. The importance of the chirality of a compound is important in the interaction phase with the target, yes, but also in other moments of the distribution of our compound inside our body. For example, it was observed an high selectivity in some membranes. Only one enantiomer is able to cross, probably. Only one enantiomer is able to use a particular transport system. And so we can observe this selectivity in a specific membrane. Selective metabolism, also in this case, our enzymes are able to metabolize specific enantiomers because they have a specific binding pocket, active site inside the enzyme structure, able to interact optimally with specific stereo enantiomer. The importance of the drug receptor interaction, we have already discussed it, to give finally the desired response. Here you can see other examples of the different biological activity of the two enantiomers. This is alpha propoxyphen. It is an open chain derivative of morphine. Only plus is analgesic, painkiller. The minus is antitussive, you know. Other compounds, this Bay key 8644. You see this is the asymmetric carbon atom. In this case, the two enantiomers have a complete different biological activity. The minus is an antagonist of the calcium channels. The plus is an activator of the calcium channels. So you see the two enantiomers are the opposite biological activity. Norepinephrine, the minus is a direct sympathicomimetic, the plus is an indirect. Okay. Adrenaline, already described. The minus is 300 times more potent than the enantiomer. Here you can see the chemical structure of a potent toxin present in specific mushrooms. Amanita muscaria is the picture. You can see very nice mushrooms. And also in this case, you see there are 3 asymmetric carbon atoms, but only 2s, 3r, 5s muscarine is potent as muscarinic agonist. 200 times more potent than the other isomers. Any questions about this point? I think you already know this type of concept, but I'd like to show you the application of this topic to medicinal chemistry. Have you any question at home? No? Yes?
Yeah, just more like a curiosity. Is there any current medical application of the toxin we just mentioned?
Muscarine, the muscarine.
Yeah.
Muscarine is a potent agonist. Now we use this compound we investigated a lot of nicotinic agonists and the muscarinic agonist to treat Alzheimer's disease. Because you know, a patient with Alzheimer's disease has a big loss of neurons. And so we try to activate the remaining neurons in the brain, with a potent agonist. And in particular, we try to use muscarine as a potent agonist, or otherwise we use this backbone to design new potent agonists. In that time, more than 10 years ago, we found different potent agonists, but the problem is, after a strong activation of the muscarinic receptors, sometimes we have a downregulation of the same receptor. This means that the receptors do not remain on the surface of the neurons, but try to go inside the neurons like a protection of the neurons from the activation by exogenous substances. And so our investigation in that time was finished. But we used this type of compound as a model, as a backbone. We took this type of backbone to try to design more potent agonists. Yeah. In that time, we went to the meeting in Holland, yes. And the picture of the meeting was this mushroom, because we were a group, European group, international group of investigators on this type of substances in that time. Yeah. And we was in competition with a specific German group, and they won the first position, and in that time we were third by Boehringer Company. Boehringer Company is a German company, and we received some money from this company. But you can imagine, Boehringer is German, the other group was German, and so the German won in that time. But we were third, and so okay, we are on the podium. Yeah. Professor Muchler, Lambrecht, it was a really, really nice group, German group, yeah. Okay. Any other questions? No? Okay. Now, okay. Geometric isomerism. You know I think, very well this type of isomerism. For example, of the 2-butane, you see we have two forms, cis and trans. In German, we say zusammen and entgegen, Z and E. Zusammen means together, entgegen, trans, the other part, the opposite part. Please, you can see this other example. 1,2-dimethyl cyclohexane. We have the two forms, cis and trans, okay. Z, zusammen and entgegen, okay. But in the case of trans, we have also the optical isomerism. So we have two forms of this trans compound. It's an exception because there is no a plane of symmetry able to cut in the two halves this molecule. Once again, you can understand how only cis is able to interact optimally interact with the receptor, and why not the trans. Once again, you see A with A, B with B, but C, in this case, is another part of the plane, and so is not able to interact. So in the trans compound, you see C is the other part, all in the cis is in C is in the right part. Here I'd like to show you an example to understand the importance of this type of isomerism. You can see the molecule of estradiol is a female hormone, is an agonist, potent agonist. Some years ago, an investigator hypothesized that the activity of this hormone was given by these two alkyl groups, and the whole carbon backbone was only a spacer. So the two most important groups are the two OH. One is phenolic. Remember this OH is mounted on an aromatic ring, and the other one you see is an alcoholic OH. To demonstrate this hypothesis, these scientists synthesized the two geometric isomers of diethylstilbestrol. Please see the chemical structure. We have a double bond here, and then two phenolic groups mounted on the double bond. So in this case, we have the two isomers, cis, when the two aromatic groups, the two phenolic groups are on the same part, and trans when they are in the opposite position. These scientists in that time tried to measure the distance between these two OH, and the distance was about 10.7 angstrom, you see. And he followed his hypothesis, and he said that only the trans isomer can be active and not the cis isomer. Why? Because only the trans isomer has the two OH groups at the same distance of the estradiol. These scientists performed in that time several experiments, and they found that effectively only trans-diethylstilbestrol was able to activate the hormone receptors like estradiol and not this cis isomer. This is a clear demonstration of the importance of this type of isomerism in medicinal chemistry. Once again, you can see the different way of the fusion of these two sex membranes. We can have a 5-alpha cholestan. We see these two atoms are in opposite position. Trans is a transfusion of these two rings. And when you have this type of fusion, the two rings are on the same plane. So the molecule is quite planar in this case. If you have the 5-beta cholestan, you see the methyl group and the hydrogen group are on the same part of the plane. So we have a cis fusion. In this case, the two sex membranes are quite perpendicular. So you can appreciate the different features in the space of these two isomers, geometric isomers. Once again, please remember the meaning of alpha and the meaning of beta. Alpha is when a substituent is under the plane. You see this proton, for example. Beta is when the substituent is above the plane. For example, this 5-member, you see this red bond. This is the chemical structure of the gossygenin. It's a toxic natural compound used for the treatment of heart troubles. Digitale purpurea. Do you remember the name of the plant? Digitale purpurea is very famous and very toxic. So we can start for 15 minutes, okay? And then we can take a cup of coffee, and then I want to show you the different type of fusion between the different rings. Okay, so 15 minutes of the break. I open the window because today is very hot. Spring is coming. Okay. Today a lot of people in classroom. It's a pleasure, really, because for me to speak on a monitor is terrible. It's like on the wall. When you speak to the wall, just a white wall, no more.
خیلی هستن ولی خب همین دیگه هم خیلی داشتیم که همش رو استرس خیلی احساس کنم خود من اصلا معمول استرس نمیشه گفتم برای مثلا 20 تا نداشتم واسه میشونم من 120 تا وارد داشتم روز دیگه نبودش اوکیه من مثلا که سال سرطان کافی همین خیلی مشکل من خیلی برای میخوام بدم زاب کامل تصمیم بخوره درس و بگه هم اوکیه باید که بیشتر دامون کمک آره خیلی قبول داری تو
ولی کلاس نفس رو خودم من هم
فکر کوچیک بود اصلا کلاس نداشتی آنلاین نداشتی صرف استودی بود
من اصلا کلاس اومدم اینجا همین اومدم بودم من میشد این حالا من دستم بودم بعدم صورت دادم بعد دیگه کلی کلاس
منم اوکیم دیگه مثلا وقتی چیزا مجبور داره شده دیگه من خیلی بدم ما همه درسان میشه
اینجا چند تا کار دارن
محدودیت مثلا ما کوچیک محدودیت داشتیم و 3 بار واقعا 3 بار بود و اینجا خودم اوکی یه بار بعد چی شد اون برو معامله خودت تست کن اگه هدف تست کردن خودت
آخه نه دیگه الان که لیمو دادن دست میشه من این سوال اینجا نقطه مهمه من که من سر کار مردم بگردم اصلا خودم اونطوری اما دی بچه‌ها رو اینجا دارم نه بچه‌ها رو بگم حالا من به چیز هم برسیم مثلا اینا که خود من میگم همشون نباید یعنی 90% درسش نباید
خب این رو قبول دارم ولی اصلا عجیب‌ترین برخورد میکنم با نمره به جوری مثلا من اصلا میرم شروع میزنم سر نمره تو مثلا آقا عجیبه این همه رو میشن میشه از وای من بعد
مثلا ببخشید خودشونه که اصلا ارزشی شدن از عمل پرنسن که بدن همین اوریج با ما مقایسه می‌کنم بچه‌ها خیلی در کار خیلی درس کنم همشون اکثر از من هیچ وقت اوریج کلاس من براشون بالا نمی‌دونم همه با هم یا مثلا همه با هم مثلا خیلی از درس می‌شدم 20 21 ولی خب تلاشی می‌کردم بعدم خیلی از سنگین‌تر نمی‌خواستم رو انجام بدم هر بیشتر من خواستم دادم دو بار امتحان دادم اول من چند تا خارجی خودشون بعد در بار من ببین دوباره رفت دوم مادرام سمت میتره یعنی برای من کاری که میفرستم من میفرستم اوکی مثلا دو تا بلد باشم تو سوال سه تا سوال رو که میگن اون رو تصمیم میگیرن بود من هر چی نمیشونم براش موضوع کافی نیست و این سری نمیتونم بدون چیز داشتیم با هم مستقیم دوباره ردیکال بکنیم یه تشکیل داد سوال بیشتر نه چه های کرونا I want to go home because I didn't bring my laptop for lab.
No worry, I'll do it.
No, I don't go. بعد دوباره گفت که کافی نیست من نمیدونم بعد خدای من همین کار کرده با
با من هم دارم میکنم که زمان حسی ندارم میزن چون من نمیدونم من چیزه بعد دفعه پیش ببینید دیگه اصلا هر چی جزوه رو نوشتم گفتم من نمیخوام بیشتر از این بنویسم امکان نداره بعد گفتم من جزوه اینجا اینم چیزی که من نوشتم تو بگو بیشتر چی میتونستم بنویسم بیشتر تو لازم یه بار دیگه ترای کن آره اوکیه من سربایی که توی شکل قراردادی سر من که استاده اینجا میگم یه پاسپورتش خدا اینجا استاده این شکل ما رو ندارم مثلا من تو که یه روز فردا میکنم استاده رو به من What? Come again. Me? No. No, he just no. We're just talking about the vacancy. She didn't say it. I thought بازی که بلایی سر من آورد بلایی سر یه روز بلایی استاد بایدن به من زنگ زد با تو تیم زنگ زد Oh, because they recognize partially. Yeah. I'm sorry, I will say this in Persian and then بعد زنگ دستم واسه خودم عجیب بود واسه اسم صدام سول بود بعد سول بعد این سولم که استادی بود که نه کل دانشگاه کوردینیتور نبود ولی کل دانشگاه قشنگ واسه همین میشد چون قشنگ میرفتی تو اتاقش این همه یه کمد بزرگی همش جایزه خیلی مثلا موجود بود یه بار روز صبح می‌زدم من یه هفته ازش براش ما سلف استادی بود اصلا کلاس نداشتیم این آنلاین هم که اینا دارن اونم نداشتیم خودمون از من زدم من تجربه یه هفته ازش مثلا یه سری سوال فرستاده بودم من نمی‌فهمم میشه برام یه رفرنسی چیزی بدی من برام بخونم یه می‌زنم یه هفته قبل امتحان بود دیگه یه هفته قبل امتحان بعدش شدم خودش رو ازم پیدا می‌کنه جواب نداد یعنی زمان your questions are just super I will not allow you to come to my exam من کلی باش حرف زدم okay now I understand you learn little bit but now I know that you can complain من چیکار من نمیتونم بیه رجیستر کنم بعدم نمیرفتی میشونی چند بکنم ببخشید در این کاری رو اوکی پس
Yes, I will go to the library, then I will go to home. I will prepare it by myself. If I have to sign off, I will just. Bye-bye.
Eccoci qua. Eccoci qua. Vediamo un attimo. So we are talking about the geometric isomerism, and in particular at this point I want to show you the difference between these two compounds, one called the cis-decalin and the other one is a trans-decalin. Decalin means 10 carbon atoms, 2 6-member rings fused together. You can see these 2 hydrogen atoms are on the same part in the cis isomer. In the trans isomer, the two hydrogen atoms are in the opposite part. I have here the model. You see the two hydrogen atoms are in the same part, you see. This means that these two 6-member rings are quite perpendicular. In the trans isomer, here you see the difference. You see the two hydrogen atoms here in the trans position, and you can see that the two cycles are on the same plane. So when you see this type of system, it's important to see the position of the substituents on the two common carbon atoms. If you have the hydrogen in the opposite part, you have the trans isomer. This means that the two rings are on the same plane, A and B. If you have the cis isomer, the two rings are quite perpendicular. So you can understand that when the trans isomer interact with the target, it has a different interaction in comparison with that of the cis isomer. In the course of medicinal chemistry 2, we will have a particular chapter on hormones, and in that time you can appreciate the importance of the fusion of the different rings in order to have an optimal interaction with the receptor. Now we have an important point. Enantiomers separation. I don't know if you have already seen this point during the course of organic chemistry. I don't know. Yeah. Have you? Yes? Oh, perfect. Because it's not so easy to separate two enantiomers, because you know they have the same chemical physical properties. And so I have to introduce an element of diversity. Enantiomers are like the twin sister. My wife is a twin sister. At the beginning, in that time, I didn't know that she had twin sister, so in that time I had a particular troubles, because sometimes my future wife talked a lot with me, in other time not, and I asked, but I wonder why sometimes she had the pleasure to stay with me and the other time, because I discovered 1 year later that she had a twin sister. Okay, a quite strange story. And if you want to separate the two twin sisters, we have to introduce an element of diversity. In other case, they remain together. Okay, so you know that the enantiomers are able to shift the rotation of the plane, of a plane polarized right, okay. And here you can see how we can separate these two enantiomers. We have to introduce an element of diversity. We are lucky because in nature we can find pure enantiomeric compounds. In this case, we have a mixture of the two enantiomers of a base and we have to separate these two enantiomers. We can make salts with an acid, and in this case we have a natural acid, optically pure, called malic acid. So if we put together, if we put in the mixture of the two enantiomers this type of acid, we have two couples of different salts, minus minus and plus and minus, and these two couples of salts have different chemical physical properties. So it's possible, for example, to have the precipitation of only one salt and the other one remain in the solution. And so if we are interested to have only the precipitated salts, we can filter off the other salts. And so when we have the crystals, we can treat the crystals with a base. Strong base is able to release the weak base, and by extraction we have the pure enantiomers. This is just to remember you how to make a separation of two enantiomers. In this case are two bases, a couple of bases, using a natural optically pure acid. Otherwise, if we have a mixture of two acidic compounds, two enantiomers, we have to use an optical pure base. Now, more recently, there are other techniques which involve the use of membranes, for example, or chromatography. It's possible to have optical active stationary phase, and so the enantiomers form different diastereoisomers isomers with the stationary phase, or by capillary electrophoresis, or by other type of techniques. Yes. Yeah, okay. Yeah, sorry. Okay. The problem is a separation, it's expensive. So the company tried to avoid the presence of asymmetric atoms inside the molecules. If necessary, they have to isolate the active enantiomers. And this means that they have to, this process is time consuming, expensive, and so on. So normally they try to avoid the presence of active carbon atom on their structure. This is the mainstream, we say, of the companies. You know, less expensive compounds, not time consuming, and so on. So normally this type of workup, the separation of specific enantiomers, is related to the research experiments, but sometimes there are several drugs on the market which needs the presence of only one enantiomer. Normally these drugs cost more than asymmetric drugs. Okay. The last isomerism that we see today is the conformational isomerism. Here you have the molecule of the noradrenaline. You see that the molecule of noradrenaline can have a lot of different conformations, you know. But why this topic in medicinal chemistry is so important? Because when we try to improve the potency, for example, of noradrenaline, it should be important to know the active conformation of the noradrenaline in order to synthesize compound with the same chemical features. Here you can see the different conformation of a very simple molecule, ethane, you see. Staggered, eclipsed, gauche, anti. We can make a study of the energy of each conformation, and if you remember, we can have this type of pattern where you can see that the more stable conformation is the anti-conformation, where the two, this is the example of the normal butane, where the two methyl group are in the opposite part. If we want to stay relaxed at home, I have two sons. I have to put the first sons in one bedroom and the second one in the other one, in the opposite position, so the system is a very low energy. If they are together, the system a lot of entropy. Okay. And what about cyclohexane? In particular, if you put some substituents on these two rings, we can stabilize particular conformation, chair conformation or boat conformation. How? Because normally this cycle try to put in equatorial position the most, the biggest, the biggest constituents. And in this case, they try to put in the equatorial position, you see, the biggest substituents on the ring. And we can stabilize the different conformation. There are exceptions, yes. Here you can see one of these exceptions when there is the formation of particular intramolecular hydrogen bond inside the molecule. In this case, we have two OH group on the same molecule able to stabilize a particular conformation instead of the anti-conformation. Okay. But how can we block a particular conformation in order to have a more potent agonist, for example, or a more potent antagonist? There is a particular strategy called frozen analog approach. It's not a low temperature. Frozen analog approach is not on a refrigerator, but we can block the both conformation, for example, by using this strange cycle called the Norbornane. Otherwise, we can stabilize the chair conformation using transdecalin, you see. So, if you want, here you can see the application in particular on the molecule of acetylcholine. You know the importance of acetylcholine. It is released inside the synaptic cleft, interact with the post neuron receptors, and so on. Okay. Here you can see the different conformations, but if you want to have an idea about the active conformation, we can apply the frozen analog approach. This means that we can introduce the residues of acetylcholine on a constrained system. In this case, you can see the rigid transdecalin analog of the chisoid conformation, or we can see a cyclopropane residue. Here you can see the trans residue of acetylcholine. In this way, we have to measure the activity of this compound in a system. We have to construct the dose response curve we have already seen from the pharmacological approach. So we have to know the ED50 of this compound, and we can compare the different potency of the different compounds. So in this way, we can have an idea about the active conformation of acetylcholine, yes. But it's not, the situation is not so simple. In this case, we have introduced a strong residue, a big residue on a small structure of acetylcholine. This means that when acetylcholine, this residue, try to interact with the receptor, perhaps this part of the molecule can block the interaction, can be an obstacle to the interaction, can change the chemical physical properties, the solubility, and so on. So, in this approach, we can have some information about the right conformation of acetylcholine, but there is an important warning. We are changing the chemical physical properties of the compound. And so perhaps the results, the information cannot be directly related to the activity of acetylcholine. Is it clear at this point? Yeah?
No, not for me.
Okay. So, no. You see here the structure of acetylcholine. Yeah? I don't know. Who is? Oh. A ghost. We have a ghost in classroom. Acetylcholine, you know, is very small. It's like a snake. And so perhaps this molecule can reach very easily its target. But the problem is that this molecule, okay, it's a noradrenaline, the same topic. But the molecule is not so rigid, it's not so frozen. So we don't know the active conformation of acetylcholine. And I need to know the active conformation of acetylcholine because I want to synthesize more potent agonists, for example. How we can know the active conformation of acetylcholine? I have to introduce a rigid element. I have to block some way the mobile structure of the acetylcholine, the flexible structure of acetylcholine. How? For example, the structure of acetylcholine can be mounted on transdecalin, you see here. And so we can block a particular conformation. In this case, is a schizoid conformation. And we can compare the activity of this schizoid derivative with that of acetylcholine. Perhaps schizoid is more potent, perhaps. It's an hypothesis. Because the acetylcholine is in the right conformation. What happens when acetylcholine is very close to the binding site? There is a mutual interaction, and perhaps also high energy conformations of acetylcholine can be stabilized. In this case, can be stabilized, and so it is necessary to have a particular arrangement of the molecule of acetylcholine to have an optimal interaction. Okay. If the molecule is already in the right conformation, you have a gain in the potency, because it's not necessary this type of arrangement of the molecule. In this case, if the schizoid conformation is the right conformation, you have a more potent result. But as you can see, the system of acetylcholine is mounted on the more lipophilic system, consistent on the 2 rings cyclohexane ring. In this case, we have changed the chemical physical properties, but also the molecule, the steric hindrance is greater. And so perhaps this molecule can interact with the target, but not in the right in the right way. Yeah. This is the problem. We have a frozen analog approach. We have blocked the conformation, but we have changed the chemical physical volume properties, and so perhaps we have not the ideal interaction. So no ratio, no. The 2 forms, the 2 molecules are too different. In fact, if you can see, other scientists use smaller cycles in order to avoid this type of problem. It's clear now?
Yeah.
Okay. Have you any other questions? At home? Okay. Okay, dear students. Here, I'd like to show you another interesting example of the frozen analog approach. In this case, this approach was applied on the molecule of dopamine. Why dopamine? Dopamine is very important in our CNS to control the fine movements. In particular, in the substantia nigra, inside the brain, there are a lot of neurons, dopaminergic neurons. During the Parkinson disease, these neurons can die. We don't know why. But in particular patients, there is a specific death of these dopaminergic neurons. This means that these patients are no more able to control the 5 movements, and at the end, they have problems with the digestion of the food, the breath, and so the problem of this disease is that the patients remain conscious. So you know exactly what is happening. It's quite different from Alzheimer's disease. Alzheimer's disease is a general neurologic death, neurons death. In this case, we have, in the Parkinson disease, we have a specific death of specific neurons. So, a therapeutic approach of this disease is to administrate dopamine to counteract the lack of dopamine inside the substantia nigra. You see here the chemical structure of dopamine is very similar to that of noradrenaline. You see there is not a OH group in this position. The problem of dopamine is that dopamine is an amine. Normally it is protonated at the physiological pH, and so dopamine is not able to cross the blood-brain barrier. It's too polar. If we assume dopamine orally, dopamine remains in the periphery, and we have only side effects, like vomiting, diarrhea, and so on. So it's not the right solution. We have the conformation of dopamine were deeply investigated. Why? In order to find an agonist, like dopamine, with increased lipophilicity, to cross the brain-blood barrier. For this goal, the investigator studied a lot the different conformation. You see, which it is a future chapter during the course. They investigated a lot of different conformation, and they found that this rotamer, alpha rotamer, is called, is the active conformation of dopamine. How they know that this conformer is the active conformer of dopamine? Please see this molecule is called apomorphine. Apomorphine is a derivative of morphine. Morphine is treated in acidic condition, and we are a rearrangement of its structure, and we get apomorphine. Apomorphine is a strong and potent agonist of dopaminergic receptors. Please, you can see in bold the chemical structure of dopamine, and in particular, you see the active conformer of dopamine. This molecule, apomorphine, is very rigid, so we have demonstrated that the active conformer of dopamine is the trans-beta conformer alpha, is called, because this rigid backbone of apomorphine, which contain the active former dopamine, is a potent agonist and is also a lipophilic, more lipophilic, and can reach the CNS. So you have seen the importance of the conformation isomerism, conformational isomerism in medicinal chemistry, because this type of investigation can contribute to the design of more potent agonists of endogenous neurotransmitter. And apomorphine is one of the main drugs used for the treatment of Parkinson's disease. We'll see this particular point in a future chapter about dopamine, and we'll see also other different compounds deriving from the frozen analog approach applied on the chemical structure of dopamine. Is it clear? Yeah? Because I think if you know the goal, it's easier to study this type of approach because you know directly the main important point. Is for me, I hope also for you. How we can change again the chemical structure of natural compounds, of endogenous agonists, in order to get more potent compounds. It's not so easy, for example, to change the chemical structure of a noradrenaline. How we can change this structure? There is a particular strategy called isosterism and bioisosterism. Here you can see the definition. Two isosteric molecules must have the same shape and the same external volume. Here you can see baclofen. Baclofen is a specific agonist of GABA receptor. We'll see this type of receptors, we'll see this type of drugs. And here you can see some change inside the structure of baclofen in order to increase the agonistic potency or to transform an agonist like baclofen in antagonists. In particular, you can see that the investigators try to change the features of the acidic group, of the carboxylic group. If you change these acidic groups with other acidic small groups, you have still agonists. But if you increase the dimension of the acidic group, of the carboxylic group, with other acidic groups more bigger, you obtain antagonists. Normally, when you put on the backbone bigger residues, you obtain antagonists. If you put smaller group, normally you have agonists. So on medicinal chemistry, normally the dimension of antagonists are bigger than those of agonistic compounds. The concept of isoster is illustrated in this picture. This is an article in Italian on Arresto del Carlino. Is the most typical newspaper of Rimini. And you see there's two guys were on a motorway and they try to sell iPhone at low price. So people, my wife probably says, like you, okay, like me, yes. On the motorway, oh, my wife, I found an occasion, iPhone only 200 euros. Oh, yes, I can buy it, it's stratospheric, you know, okay. So you pay, you get a box. It's my iPhone and so on, okay, I go at home and then I try to use it and so on, okay. When you are at home, you open the box and you find two rocks with the same weight, the same dimension of the iPhone. This is the concept of isomerism. We can change the nature of the chemical compound inside, but outside remain the same volume. In this case, in the boxes of the PCs, there were bottles of water. Okay, it's no rocks. Okay, no brick, it's a brick, yeah. Okay. When this concept born, in the 1916, you see, this guy Langmuir, a very famous scientist, investigate the properties of two very common compounds. Carbonic aldehyde and nitric oxide. You can see in the table the different physical properties. Total electronic charge the same, 22 electrons. Molecular weight the same, viscosity, critical pressure, critical temperature, thermal conductivity. All values are quite the same. And Langmuir thought, if these two compounds have the same chemical physical properties, perhaps they have the same biological activity. This was the starting observation of this approach. Later, you see, 1925, Grimm extended the concept, allowing a wider manipulation. Here you can see the application of Grimm. You know that carbon has 6 electrons. And nitrogen has 7 electrons. He said, perhaps it's possible to change a nitrogen atom with a carbon with a nitrogen, because you have the same number of electrons. Oxygen has 8 electrons. Perhaps we can chain oxygen with a nitrogen, with a hydrogen atom, or with a carbon with 2 hydrogen atoms. You see? We maintain the same number of electrons, external, by adding hydrogen to the atoms of the other line, the other column, sorry. In 1932, LMI hypothesized that the total number of electrons was not important, but their arrangement in the outer set. Okay. So more elements, you see, phosphorus, silicium, sulfur, but the approach, the strategy is the same. We add hydrogen to the element of the other column, of the previous column. Some years later, a development of this strategy was to consider the aromatic rings quite equal, and so we can change a benzene with a thiophene, pyrrole, you see, pyridine, and so on. But how this approach was applied? Why this approach is so important? You can see here an example. Aminopyrine is a basic compound. You see this nitrogen atom, this heterocycle. It is a good painkiller, but it has a problem. It can cause a cancer. Why? Because this nitrogen atom can be oxidized, and the oxidized form can interact with the DNA of the cells. This is the problem. So they apply the isoster approach on the nitrogen. You see, the nitrogen was substituted with a carbon with a hydrogen. And we get propifenazone. Propifenazone is a good painkiller without any problem, without any interaction with the cells. So it is not cancerogenic. You can understand the importance of this approach. We can change some atoms because we had problems with the metabolism or with the toxicity and so on, and we can maintain, hopefully, we can maintain the activity. In 1951, Friedman developed additionally, deeply, this concept, transforming isosterism in bioisosterism. You see the hypothesis. The number of electrons is not an essential feature. The groups that replace the original group of a molecule maintain their activity are bioisosters. So you see a wider application of this concept, non-classical isosters. So the ketone group, for example, the carbonyl group, can be replaced by a sulfoxide, a sulfone. The acidic group, carboxylic group, with other acidic groups. The OH with other group able to give hydrogen bonds. the halogens with the trifluoromethyl and other groups, and the pyridine rings with the nitrobenzene or the protonated pyridine rings. Here you can see a summary of this approach. But here we can see some application of this method. Decamethonium. Decamethonium is a compound with two quaternary protonated nitrogen atoms, permanent charged nitrogen atoms. This compound is able to interact with the muscle, and this compound is able to block the muscle contraction, interact with the receptor of the acetylcholine receptor in the neuromuscular junction. The problem of decamethonium is that this molecule is metabolized very slowly. So, after the surgery, you remain a lot of hours on the bed without forces, with a problem with the intestine muscles, movements. And so the scientists try to decrease the shelf life of this compound. How? They applied the bioisosterism approach. If you see, they changed 4 carbon atoms, 2 were transformed. Okay, they introduced 2 ester groups, but you see 2 carbons are displacement with the oxygen atoms and the other one with a carbonate. So they introduced 2 esters groups inside the structure of decamethonium. The distance between the 2 nitrogen atoms remain the same because it's critical. So the chain, it's important only because it behaves as a spacer. But in this case, they get succinylcholine. Succinylcholine is very fastly metabolized, hydrolyzed in particular, on the 2 ester groups. And so the shelf life of succinylcholine is shorter than that of decamethonium. This means that after 1 hour of the surgery, you are able to walk, to go away. This is an application, a particular application of this approach to an important molecule such as decamethonium. We have a safer drug with optimized physicochemical pharmacological properties. Second example, indomethacin. You see here on your left, indomethacin is the most potent anti-inflammatory drugs. But the most potent means also the most toxic, especially on the liver. And the scientists try to maintain the same activity, but by decreasing the toxicity of this compound. Some years ago, Sulindac was introduced on the market. Sulindac demonstrated the same activity of indomethacin with a less toxicity. Why? First of all, you see this amide group this amide group, you have a free rotation of these residues, and the scientists try to block the active conformation of the indomethacin with a double bond. They introduced a double bond, and they found that the active configuration isomer, geometric isomer, was the syn, you see, zusammen, Z isomer, the two aromatic rings in the same part of the molecule. And this was the first point. They found the right conformation of indomethacin. And the second point was the addition of the sulfur group instead of a chlorine. Sulfur is a electron-rich atom, you know. It's able to block, to act as a radical scavenger. They was observed that during the treatment of indomethacin, there was a severe hepatic toxicity due by the formation of free radicals. So the investigators introduced the sulfur atom to limit the formation of toxic free radicals, and in this case, sulindac is now used as potent anti-inflammatory agent instead of indomethacin. So we have seen how we can apply this type of concept to increase the activity and to reduce toxicity of particular molecules. Have you any comments, any suggestions? Do you understand how to apply this type of concept, approach? Just a moment. 2, 3, 4, 5. Last 5 minutes just to introduce this important concept, and then we will treat it in the next lesson, next Monday, okay? Because you have lab during this weekend, so we will see you next Monday. There is an important term used in medicinal chemistry as in pharmacology. The word pharmacophore. Pharmacophore is the minimum chemical structure able to give a particular biological activity. Why this concept is so important? Because we can minimize the complex structure of particular compounds, maintaining the same biological activity. So we can use a less complex molecule to have the same result. Here you can see the chemical structure of heroin. Heroin is a derivative of morphine, we'll see. But now it is important that you see the complex of this chemical structure. And so you know heroin derives from morphine, morphine derives from opium, Opium derives from Papaver somniferum, you know. During the Second World War, all the India, Bangladesh, Pakistan, the Asiatic region were under English soldiers, if you know. And in that time, the German soldiers needed a lot of painkiller. You know, we are on the first line, we are in war, you need painkiller to treat the different problems in the first line, you know. And so in that time, German scientists tried to simplify the complex chemical structure to heroin to have synthesized an organic, easier, smaller compounds with the same activity of heroin. They simplified the chemical structure of heroin and they synthesized methadone. Methadone is less complex, it is easier, it is easy its synthesis in lab. The chemical synthesis is very easy. And methadone has the same potency of morphine, has also the same side effects, of course. But methadone was synthesized in labs. In that time, we had tons of this compound. And so it's possible to treat the pain of the different soldiers in the first line. Methadone now is no more used in therapy as painkiller, used for the treatment of heroin, you know, in the people who use this type of compound to reduce the effects of heroin. So we'll see these substances, we'll see this type of approach, but methadone represents the pharmacophore, the minimal chemical structure necessary to have the painkiller activity of heroin. So, have you any questions? Have you understood it? Please, yes, Mona.
So, just to check if I understood well, whatever we do to a certain molecule, we should not change the pharmacophore, because in that case we will have different or no effect.
Yes, okay. It's not so easy, this type of operation. Sometimes you get another molecule without activity, yes, of course, or you can amplify the side effects. It's also possible. And so it's not an easy operation, but it is important to try in order to have a more accessible chemicals. To have compounds that can be synthesized more easier in the lab. And so you can have tons of compounds. For example, you cannot have tons of heroin because you need a lot of papaver somniferum and so on. Methadone can be synthesized in lab and you can have tons of this compound.
But,
yeah.
how does the scientist usually know for each drug what is the pharmacophore?
Like, you have to investigate this point. It's not so easy.
Yeah, I mean, it takes so much time to study.
Yeah. You have to try, for example, okay, at this point I try to use another substituents in this position, more simple. and then I try to substitute this ring with another chain. It's not so logic, but normally the scientific investigation needs to develop this type of studies. For example, you can work for 5 years only on one modification, but you can contribute to the whole investigation about the molecule of heroin, for example. Yeah, it's not so easy. And we'll see how we can simplify the structure of, this is morphine, you see, very complex. And I will explain you the chemical structure, and I show you how it is possible to open the ring of this molecule in order to have methadone. It's a strategy of simplification, chemical simplification of the molecule of morphine. Very nice. Other questions, comments? Yes, Jude?
So, well, this is just for curiosity's sake. Those drug laws.
Drug?
Those drug laws.
Yeah.
How are they able to just come up with these kind of productions? Because all they know is they have no scientific background. They just mix compounds and then they have, let's say, pure, the impure cocaine and all this stuff. How do they make them up? Because they have no scientific knowledge in what they are doing. All they know is the final products.
So, do you mean about synergistic effect?
Not really.
No. So you want to associate two different molecules to decrease the concentration of each one? I don't understand.
I mean those drug laws, like the Mexican drug laws and all these people. They have no scientific background.
Yeah.
All they know is mixing compounds, putting the compounds and then coming up with the final products, let's say the cocaine and all this.
Mm-hmm.
So without all this scientific background, how are they able to come up with things of these sorts?
If you mean to change the chemical structure of some drug by put together with other substances.
Yes.
So this is an example. Morphine has two OH groups.
Yes.
Heroin was synthesized by Boehringer in Germany 200 years ago. They mask the 2OH group in order to increase the lipophilicity. Because they thought, if we increase the lipophilicity, we increase the activity in the CNS. Not so specific at that time, but they tried with acetylsalicylic acid and they have a success. And they try also to apply the same approach to the molecule of morphine. And in that time, they found that heroin has, I think, 100 times more potent than morphine. Heroin is able to cross very easily the blood-brain barrier because you see there are two ester functions, but when it arrives inside the CNS, it should be transformed again in morphine by hydrolysis of these two bonds. So you have morphine again. This is a strategy. This is the reason. Because people transform morphine in heroin. Because if there is no a money reason, you cannot work in a lab, and you cannot transform morphine in heroin. They transform morphine in heroin because with 100 grams of morphine, you get 150 grams of heroin, but heroin is more potent and so it is you can sell few milligrams of heroin, and you get more money than to sell morphine. This is the reason.
So it means those people who do such productions, or there are scientists or people of there are scientists behind.
Yeah.
Okay.
Yeah. Bad scientist in this case.
Yes.
This,
Yes.
this is the reason. And when you see on television, oh, this is a lab of heroin, you see a lot of acetic anhydride. Acetic anhydride is used in this type of reaction. You see a bottle of this reactive in the lab, inside the Amazon forest, where you want. You know, in Pakistan also, a lot of bottle of acetic anhydride. Oh, bad scientist. Okay, any other questions, comments? Atum, have you any questions? No?
No, it's all clear.
Okay, thanks. So next time we start again from this point, and I think we are almost at the end of the introduction part, and then we start with the chemotherapeutic part of the program. Okay? Okay, dear students, thanks a lot. Have you a nice lab this week. And we see you next Monday afternoon. Okay. Bye-bye. Bye-bye, dear student, also Tom. Ciao. Okay. Yeah. Yeah, okay. Yeah.
Everything on
Yeah, just a moment.
Including today's one.
Yeah. Okay, now I don't know if I have all the okay, I have the introduction part you see here.
Yes.
Okay, you can put this one in.
Can you add today's one to it so that it will be the complete one?
Okay, here, okay. Color. Ciao, bye bye. Bye bye.
There is this question I want to ask.
Mhm.